My name's Tony Cinnamon. I work out of the Chicago office. I am the coordinator of the Windows Curtain Wall Skylights TRG. I've been with the company for 18 years now and do a lot of work on windows and curtain walls. And today we're going to be talking about an in-house research project that we embarked on, well, starting actually a few years ago and actually culminating last year. We came to it in a roundabout way. It actually started with an actual project and actually then turned into an in-house research project. So in regards to the learning objectives today, our project has to do with the strength of damaged in-service glass. And so just as by way of review, we're going to review some of the basics of glass properties, and also we'll identify glass types, understand some glass strength standards, and how the surface damage may or may not affect the glass strength. And so our outline today sort of follows those learning objectives. We'll talk about glass basics. We'll talk about the actual glass damage and the actual project that we worked on that this was born out of. And then we'll get into the actual testing and the in-house research that we did. So for glass basics, glass takes many different forms, and it looks and can take many different colors, but it's really a lot composed of the same material. So typically what we see in the industry and what you see in the vast majority of building windows and curtain walls today is what's referred to as soda lime glass. And the basic constituents are here on the screen. Mostly it's made of sand, soda, and limestone with a few other materials thrown in. The contemporary method for fabricating windows was invented in 1952 by Alistair Pilkington, and Pilkington Glass is actually still around fabricating glass. And so from left to right, you can see it starts out with the raw material storage. So the raw materials that we just talked about goes into a batching plant and then into the furnace. And basically, furnaces at glass houses run 24 hours a day, 7 days a week. And it's extremely difficult to get them fired up. And you know that for whatever reason, if a furnace in a glass house is turned off, they're probably going out of business because it takes so much energy and effort to get that fired up. So those materials go into the furnace and become molten glass. And they come out of the furnace and they're floated on a bed of molten tin, which helps to create the flat glass. And once it goes through and goes through on the molten bed of tin, it goes into what's called an annealing layer. And it's basically a long chamber where the glass is cooled slowly, so it prevents any significant stress from building up in the glass. Then there's an inspection point, and then cutting and storage. So in regards to the actual glass industry, there's only 5 glass manufacturers left in North America, and these are the manufacturers that actually float the glass. Then that glass is sent to glass fabricators, and glass fabricators can do a number of different things. They can fabricate IG units. That could be where your low E coating is applied, whether it's laminated, that's where it will be done. And then that product then is passed on to the curtain wall manufacturers and then on to the installer, onto the job. So there are 3 main glass types. There's annealed glass, which is the process we just talked about. That's governed by ASTM C1036. There's heat strengthened glass, which is about 2 times as strong as annealed glass. And then there's tempered glass, which ends up being about 4 times as strong as annealed glass. And heat strengthened and tempered glass are governed by ASTM C1048. So annealed glass, like we talked about, it exits the float tank and it slowly cools to reduce any of those stresses. You can cut it, drill it, grind it, polish it in its current state. The issue with annealed glass is, as you can see in the highlighted square there, it breaks into relatively large fragments. So when it breaks, it's dangerous. And so for obvious reasons, then it's not considered safety glazing. So for heat strengthened and tempered glass, generically known as heat treated glass, You would then take that annealed glass after it's through that process, after it's been cut and all that, and then send it back through the furnace. And the furnace is typically at about 1100 degrees, give or take. And then it goes through that furnace again, and then it's quickly quenched with air coming out the other side. And what that does is really locks the surface, the outside surfaces, into compression to give greater resistance to thermal and mechanical stresses. So just quickly looking at what that heat strengthening process looks like, starting in the upper left, that's your basic annealed glass that's coming from one of your fabricators. It's going onto a cutting table that's basically a giant, almost like a giant air hockey table. It's got lots of air jets on it to make the glass easy to move, and then it can be cut there. Then it's stored, and then the edges are actually ground or seamed to make sure you're getting rid of any imperfections that might be on the edge that might cause some breakage once you go through the heat treating process. And then in the upper left, it goes through the furnace. And you can see that in some cases that furnace can be quite long. Depending on whether you're making heat strengthened or tempered glass will depend on a lot of different factors. The heat in the furnace, the length of time it's in the furnace, but also the amount of air that it's used to quench and the pressure at which the air quenches it at the end. And then at the end, once it's done, it actually comes out on the rollers, and you can see that diagonal board there, which is called a zebra board. And they use that just sort of as an unofficial way to see if there's how much roller wave distortion might be in that glass. And we can save roller wave distortion for an entire webinar another day. But heat strengthened glass, or kind HS, part of the reason that we use heat strengthened and tempered glass is that the surface compression that's locked in then helps to prevent any flaws in the glass from propagating, whether it's a scratch or a small chip. Like I said, it ends up being about 2 times as strong as annealed. It still breaks in relatively large fragments, so it still is not considered safety glazing. And the issue with heat strengthened or tempered glass is that you cannot cut it after it's been heat strengthened, or it will break. So we move on to tempered glass then. You can see there in the highlighted box that it breaks into very small pieces, and lots of us have seen this in different applications, your windshield and things like that, or shower doors. So tempered glass is used as safety glazing because it breaks into relatively small, sort of dice-like pieces that don't have sharp edges, so that are relatively harmless. And again, like heat strengthened glass, you can't cut it or drill it after tempering because it will shatter immediately. So with heat-treated glass, you end up, like we talked about, with a compression layer basically on the top 2 surfaces and along the edge, and then obviously for equilibrium, and there's a tension area in the middle. So that compression layer, or what we refer to as the residual compressive surface stress, it ends up being different for each type of glass. The stress amounts you see here are again governed by those ASTM standards. So annealed is anywhere below 3,500 psi. The heat strengthened there in the middle then from 3,500 to 7,500, and the tempered from 10,000 and above. And you can see that the compression layer comprises about the outer 20% of the top and bottom surface there, with the tension layer in between. So the idea being is that in order for that glass to break, that flaw typically has to get down into the tension layer in order for that to break. And also, just as a side note, some of us have dealt with nickel sulfide inclusions, and that's typically, again, that nickel sulfide expands into the tension zone and releases that tension and causes the glass to break. So next, we've covered our glass basics here. Next, we'll talk about the actual damaged glass that we looked at and the project we were involved in. The project is actually in Austin, called the Alta Vita building. It was completed in about 1987. It's 22 stories, glazed with fairly straightforward IG units. And there was a storm event that carried high winds and precipitation with it on May 14th, 2008. So you can see this stretches back a few years. So this image from Google here, you can see on the sort of the lower right there is the Alta Vita building. And on the left-hand side, you can see another building. It's actually a residential condominium building that's almost about twice as tall as the Alta Vita building. And at the time of the storm event, that adjacent building was under construction, and it had reached about the level of where that red line is. So you can see that the storm itself caused quite a bit of damage. And the way that it did that was there was quite a bit of, obviously, construction material on that adjacent building that actually blew into the Alta Vita building. And you can see that from the photographs, there was some fairly extensive glass damage to our building and some obvious breakage. So the Austin office was involved in this, and they did an initial survey of a lot of the breakage, actually the very next day. And based on the inspection that was done, we believe that the outboard light was a heat-strengthened unit, and the inboard light was a tempered unit. So you can see in the upper right there, the breakage pattern on that is pretty consistent with what we saw on the heat-strengthened glass, and certainly the bottom is consistent with tempered glass. Certainly, I wouldn't want to be sitting at that desk at the time of the storm event. That may end up in a lost time injury, and we'd lose our good record. So, obviously, there was some dramatic breakage of glass there. There was also quite a few other areas where there was some more subtle damage to glass, and that damage included scratches and some pits in the glass. And so you can see an example of that here in the upper left that's circled with a wax crayon. It's a slight pit there in the glass. And so they started to remove this glass in order to replace it. And so we were actually retained, so Matt Carlton from the Austin office actually got myself and Jim Hauk from the Chicago office here involved in the project. And we were retained on behalf of the general contractor that was working on the adjacent building at the time. And there was an opposing consultant that was actually working for the building and for their insurance company. And the opposing consultant had done quite a few inspections of this more subtle damage, the scratches and the pits. And their conclusion was that all of that glass needed to be replaced because the damage had reduced the strength of the glass, not really providing any kind of analytical backup for it. It was strictly their opinion. We, on the other hand, said, we think, we ought to at least test some of this glass to see if that's actually the case or not. So they went about replacing a lot of this glass, and as they did, they took about 35 of the IG units and placed them in storage while they were trying to decide what to do, all the time still replacing glass on the building. So we went in and documented the glass that was removed and placed in storage, and took some regular photographs, but also took some close-up, macro photographs of all the damage here, and you can see that on the right-hand side there with a scratch that was from close-up on the glass. Well, they kept progressing and replacing glass, and without any real resolution. Well, so the conclusion to the project occurred about 2 years later, I think, and all of the damaged glass was replaced. No testing was ever performed. Basically, no one wanted to pay for the testing. We talked about it and worked up some costs for it, and no one wanted to pay for it. So the stored glass was going to be discarded. And so we had talked about during the project, obviously doing the testing on the glass, and we thought, well, hey, if they're just going to discard the stored glass, maybe we could have access to it, and we might test it on our own as an in-house research project. So, being the large glass geeks that we are, we got really excited about that. So Jim Hauk and I from our office in conjunction with Mark Schmidt in the Northbrook office, we put together a proposal to do some in-house research and sent it up to Northbrook, and I think it was even it was processed and approved maybe even that same day. So we were actually very excited about that. And so our primary goal then, with the glass that we had, with the damaged glass, our primary goal was to find out that when we tested it to failure, did the fracture origin actually correspond to the damage? So in other words, does it break at a location of damage, or is the fracture origin somewhere else? And also, based on the opinions of the opposing consultant on the project, we wanted to at least verify the current strength of it. And did it meet ASTM E1300? E1300 is the design standard for load resistance for glass. So if you're trying to determine, a thickness or type of glass to use in a building, ASTM E1300 is your guide for that. So clearly, the nice part about this is that because it was in-house research, we were verifying the strength based on the current version of E1300. Obviously, we don't know what the strength of the glass was that day when it was put in about 20-some years ago, but at least we could verify the strength to see if it met what E1300 would say today. And E1300 is actually originally was based on thousands of glass lights that had been tested actually by another glass fabricator, but they've been based on annealed glass. And so part of what we were very excited about here was that not a lot had really been done with heat-strengthened glass. And so we were very interested to see where the heat-strengthened glass might fall. Now, we also had the tempered lights inboard, and we felt like there was probably something to be done with that too. So one of our secondary goals then was to look at what we called weathered glass or in-service glass. Even glass that's on an inboard light is considered to be weathered or in service because it's still exposed to air, moisture in the air, different temperature swings and things like that. And E1300 is actually based on the theoretical strength of weathered glass. So we wanted to see just kind of where it stands, where it compares to that. So we had about 30 of those lights transported up to Northbrook, and they were varying sizes, but we had about 18 of them that were all the same size, so we felt like that was a good sample size, and also based on what we'll see in a little bit, building a chamber for each size was not practical. So we took those insulated glass units and we actually separated them into the separate lights. There were 18. We ended up with 18 outboard lights and 16 inboard lights. And the reason we ended up with 2 less inboard lights was due to some breakage and other things during transit and during when the IG units were separated. So the primary participants in our in-house research, like I said, were myself and Jim Hauk. From Northbrook, Dave Folletti and Dan Weatherington helped us out a lot with the actual testing, and Roger Pelletier from Northbrook did a lot of work actually constructing the test frame that we used for our testing. There were 2 other gentlemen that were involved in our research project, and they're actually from Texas Tech University. One of them is Scott Norval, and he's the department head for the School of Civil Engineering at Texas Tech, and Stephen is actually an associate professor in the School of Civil Engineering. Scott Norval was actually involved in the Austin project. We were retained by like I said, by the general contractor. Scott had actually been retained by the formwork subcontractor because it was actually some of the formwork that they were using on the adjacent building that had actually crashed into the building that we were looking at. But also, Scott and Stephen are considered some of the gurus in the industry as far as glass testing and sort of hardcore glass engineering. They do a lot of this down at Texas Tech, and so we felt like because they were involved in the initial project, and also they've got a lot of experience with this, we felt like they were good people to have involved in our research project. So the first thing we did after we had those IG units separated was the first thing to do then is to measure that residual compressive surface stress. So the way you do that is by using what's called a GASP, or a grazing angle surface polarimeter. And the two, in this photograph, you can see the two sort of main elements are the display screen here, and then there's a dial indicator here that that you can turn. And so what you do is, here's a close-up view, the display screen, and you can see on that display that there are two, dark diagonal lines. And what you do is you take that dial and you turn it until those two dark diagonal lines are parallel with the lighter diagonal lines, or what they call the rectal lines. And that, and then I'll show you in a minute, is how you read off your stress. The way the GASP works is that it actually uses a laser that goes through a prism and actually travels along the surface of the glass and then back up and through another prism into the the body of the GASP and then onto the display. And I won't be able to describe it any further than that because it was invented by people way smarter than me. But that's the way you can read so then you read your angle actually off of the dial gauge that we saw, and then on the right-hand side is an example of on the left-hand side of the column is the angle, and then with it is an adjacent stress that you read off in PSI. Now, Stephen and Scott actually had another instrument to try out here. The GASP is fairly reliable. It's been used for quite a few years to measure that. They actually had another gizmo. It's called a scalp, which is short for a scattered light polariscope. And at WJE we talk about black boxes sometimes. Well, you can see this is literally a black box. It has a black box and a red button on it, and it sort of doesn't get more cliche than that. But it goes directly into a laptop, and you basically press the red button, and you can get a thickness of the glass, and it will also tell you basically the full depth, the stress through the full depth of the glass. I mention this only because we were sort of using it on a trial basis. We ended up finding out that the scalp really returned some wildly different results, even when you had it in the same place on the glass and pressed the button, say 3 times in a row, you would get 3 different results. So we didn't move any further with that, but I just I put it out there just as an example of some other things we were doing there. So in accordance with C1048, you measure the RCSS at these 5 locations. This is a plan view of the glass, and so you measure that stress at each one of these 5 locations, and then basically take the 5 and average it, and that gives you your average stress. So we started with the outboard lights, and so we were looking at our GASP measurements, and we were finding that we were getting much lower stress RCSS values than we had anticipated. Originally, we thought that those outboard lights were heat strengthened based on the breakage pattern that we'd seen, when we actually found that it was actually annealed glass. And you can see here the stress levels that we found were 580 to 1085 psi, which is markedly less than the 3500 psi minimum for heat strengthened glass. So we ended up finding out that this was annealed glass, not heat strengthened glass, which really didn't alter our plans too much, other than we were a little bit disappointed in that we wouldn't be able to provide any kind of data that we thought we would for heat strengthened glass. But we forged ahead with the testing of the annealed glass, and so what we did, you can see on the left here, basically took each piece and inspected the damage and documented exactly where it was and what type of damage it was on each piece of glass. And so you can see we sort of did that on some survey sheets there on the left. And then on the right, you can see that's a piece of our glass. And because we're very interested on the annealed glass in finding out where the fracture origin is, we don't want the glass just completely breaking and falling apart. So we took some clear plastic tape and used it sort of in the crisscross pattern you see there and put that actually on the compression side of the glass, so it wasn't providing any kind of additional strength. But place that on there to try to retain the glass so that we can at least see the fracture origin. So this is the test chamber that we have that we have up in Northbrook, and I guess I should have mentioned too. All the testing was done up in the lab in Northbrook. So this was the test frame, and the test frame is actually defined in ASTM 997 as to how to construct it and what kind of materials to use. And Roger and Dave and Dan did a really nice job of putting that together for us. So you can see the base. So then our piece of glass is put in there. It's retained by the frame that's around it. It's got rubber gaskets inboard and outboard and typical setting blocks like you'd have in a normal curtain wall or window setting. And also so we actually tested the glass to failure. And as you can see here, this was the breakage pattern we got, and luckily our tape job actually held. There is video of this. If you'd like to check it out, please go to the Windows Curtain Wall Skylights TRG site. I believe it's under the Technical Library, and if you go to in-house research or in-house project, you can actually watch the video of this being tested. We also measured, with an LVDT, we actually measured the deflection at the center of the glass. So we basically put a vacuum on the glass and ramped it up and basically took readings of the deflection and then also of the load at which the glass broke. But so for the annealed, we were very interested in where the fracture origin was. And so sometimes that can be tough to track down, but what you're looking for is what's right in the middle of that red circle there. It's a small area. It's very smooth. It's usually sort of a bit of an oval shape there. But that was actually, in this particular case, that one ended up being the fracture origin. And so taking a look at one of the primary goals of our research was to find out, well, does the fracture origin correspond with the areas of damage? And we found something that was very interesting. And out of the 18 samples that we tested, in only 2 cases did the fracture origin match an area where there was surface damage. And those two drawings are what you can see on the right. So you can see sort of that red square with the green square in the middle of it. The rest of the samples ended up looking like the 4 that you see on the left, where the red square defines where the fracture origin is, and then you can see the other types of damage in there. The blue are typically scratches, and then the green is some kind of a pit in the glass. And so you can see that in the vast amount of cases here, the fracture origin did not match up with where the damage was. So the other results that we found when we tested the annealed glass was at fracture, we got deflections anywhere from 0.3 to 0.75 inches. The interesting thing then was we found that was our pressure or our load at the breakage varied based from light to light from 52 to about 130 PSF, which all ended up being greater than the 40 PSF load resistance that you would calculate per ASTM E1300. So not only did we find that the fracture did not correspond to the damage in most cases, but also, at least using the current E1300, that the strength of the glass still exceeded the load resistance, even without any type of load sharing. In IG units, there's a certain amount of load sharing between the outboard and inboard light, so that the load that comes in through the outboard light is shared. A certain amount of that is shared by the inboard light. Here in the testing that we did, we were testing we were testing the lights separately. So even on its own, the annealed lights exceeded the load resistance that you calculate per A1300. And another interesting thing that we found is that the higher RCSS didn't necessarily correspond to higher pressure at breakage. So we moved on to the testing the tempered glass, and for this one, because these were the inboard lights, they didn't have the, they didn't have the surface damage like the outboard lights did. But like we talked about earlier, they're still considered in-service glass with some weathered characteristics. So we felt like as long as we had those tempered lights, we should test them to see where they came out. And so you can see this is one we actually laid down on a table just to kind of see the breakage pattern. So again, we tested using the GASP, and we found that the RCSS was 12,000, ranged from about 12,000 to 14,000 psi, which is greater than the 10,000 that would put us into the tempered range. So we were satisfied that we had fully tempered glass there, and on those we took all of our all of our 5 measurements, and put those into the same chamber and tested those as well. Now, the photograph you see here, I actually have to credit to Jamie Wild because he took this photograph. He stopped by one day when we were doing the testing, and I highly encourage everyone to check out the video of the tempered glass, because the testing of the annealed glass, it kind of breaks, and it's held by the tape, and it's not very dramatic. When the tempered glass breaks, it's kind of like a bomb goes off in there. The glass completely shatters, as you can see here, and I think Jamie was a little caught off guard by that and managed to, just by survival instincts, snap that picture when we had one break. But I highly recommend you go to the TRG site and check that out, because it's worthwhile. So the results in the tempered, you can see the deflections we found. Again, the pressures we got at breakage were from 319 to 460, which again were significantly greater than what the load resistance would be required by E1300, which is about 159 PSF. And again, we found the same things with the tempered, is that even without any kind of load sharing, we were able to, that light all on its own was able to exceed that load resistance. And again, the higher RCSS did not necessarily correspond to the higher pressure at breakage. The conclusions on our tests and our in-house research for what we thought was heat strengthened but turned out to be damaged annealed glass was that the fracture did not correlate to the location of damage, and that the damage, we felt like, at least did not reduce the strength below the load resistance calculated, at least in accordance with current ASTM E1300. And the same with the tempered. We found that being in service for 20 plus years at least didn't bring the strength down below current version of E1300. So this is the part, I guess, where I need to thank the Academy and the members of the foreign press for all their help with this. Certainly there's some people I'd like to thank for this. I certainly didn't do this on my own. Like I said, Jim Houck was involved and really appreciated his guidance on this, and he really took the lead on a lot of the sort of the hardcore engineering part of this, as did Mark Schmidt. We've got 2 papers actually that we've developed from this testing. One of them is posted on the portal now, and with another shortly to come. And Mark was instrumental in helping us with some of the numbers there. Certainly, in regards to the actual testing, Dave Folletti and Dan Wetherington did a great job helping us out with the actual test. I mean, we were in Northbrook for a full 4 days, and they did a really nice job keeping things moving. Thanks to Roger for putting the frame together and coordinating the whole thing. Jose Beltran, also in Northbrook, helped out with some of the separating of the IG units. And then Tommy Lee in the Austin office was, he was sort of on the ground floor of this when we decided to, get this glass crated and shipped up to Northbrook. He was a big help down there. And then certainly to Harry, Howard, and Mike for approving the in-house research project and, sort of having the faith in us to move forward with it. And hopefully we got some good results out of it. And then, of course, to Scott and Stephen from Texas Tech, who also helped us, crunch some of the numbers afterwards and reduce some of the massive amounts of data that we had from some of the testing. So with that, my part is finished, and we've actually finished up a little bit early, so I will, if there are any questions.
So, Tony, we've already got a few questions that have come in during the presentation. So, the first one says, how is the thickness of the glass sheet attained or controlled?
During the process, I believe the thickness of the glass will depend on how much of the molten glass is released into that tin bath, and then I think they've got various ways of controlling that when it comes out of the furnace.
All right, thanks. The next question says, you mentioned that heat strengthened and tempered glass are stronger than annealed glass. What type of strength are we talking about? Tension, flexure?
So as you saw in the presentation here, then really what provides the strength is basically that residual compressive strength, and it basically, when it comes out and it gets quenched, it gets locked in a high state of compression, and that gives greater resistance to, like I said, to the thermal and mechanical stresses, but also gives you greater load resistance as well.
All right. The next question says, based on the test results, what would be your recommendation for the Austin building? Would you replace any of the glass?
Well, the one thing that we didn't touch on in this presentation, and that we did actually talk about during the project, mainly what we've dealt with here today are more of the engineering end of it, or the numbers end of it, and the strength portions of it. One of the things we didn't talk about was the aesthetics, and that played a part too in which what lights of glass got replaced. ASTM C1036 has a whole section related to acceptance of glass. Now, it's acceptance or visual acceptance of new glass. There isn't a standard for for viewing or determining condition of in-service glass like this, and that's one of the things that we're still kind of wrestling with and here. So, from a strength standpoint, I think we were, what we saw here was that the strength wasn't really diminished. I think there probably still would have been some that would have been replaced, based on an aesthetic point of view, that just had, if they had too much surface damage, too many scratches, they would have been replaced from an aesthetic point of view.
Okay, thanks. We have another question. Did we see damage on other facades of the building, or just on the facade adjacent to the building that was under construction?
That's actually an interesting question, because that was one of the one of the contentions that we had during the project. Actually, was that this more subtle damage, the scratches and the pits, it was obviously it's much more difficult to prove that damage was actually caused by the storm. And what we found was we actually did some inspections on other facades of the building that were, that particular facade that was impacted the most was the west facade. We actually did, I think, 1 or 2 drops on the east facade, so on the completely other side of the building, where we saw similar types of damage. And so that was always a point of contention as well, that that unfortunately never got resolved.
All right, great, thanks. So Tony, it looks like that's all the questions that we have for today. Is there anything else that you wanted to add before we signed off?
Yeah, actually a couple of things. One is, if you have an idea for an in-house research project, I highly suggest you put it on paper and get it up to the powers that be. I found this to be very valuable just for my own knowledge, but obviously it has a greater impact on the work that we do, and actually has a direct correlation to some of the projects that we work on. Plus, dare I say, it was actually fun. And also, I would again encourage you to check out the videos on the Windows TRG site, especially for the tempered glass, because like I said, it's worth it.